All right, this lesson is on gravitational potential energy. Specifically, what we're going to learn by the end of this lesson is how to calculate how much gravitational potential energy is being stored in the Earth's gravitational field. So before we get started with talking about calculating gravitational energy, it's really important that we understand what it is and where it comes from. So gravitational potential energy is called potential energy, similar to the way we would call a spring's energy potential energy. So when we're talking about stretching a spring, we're talking about storing energy in that spring because there's a potential for that spring to move when released. Energy is the stuff that either makes things go into motion or gives things the potential to go into motion. So gravitational potential energy is a lot like a spring because it's energy that gives objects the potential to move. Now that energy that gives objects the potential to move isn't actually stored in the object itself. It's really stored in the Earth object system. It's actually stored in the Earth's gravitational field. So I want you to think about the Earth's gravitational field as if it's a spring that can be stretched and compressed. When an object is on the ground, that should say on the ground. Oh gosh, I gotta fix that or it's gonna bug me. When an object is on the ground, there we go. It's almost as if the spring is not stretched. So I'm gonna make that note in the picture. Not stretched spring. The Earth's gravitational field is almost like this invisible connection between the object and the Earth. And when that connection isn't stretched, there's no gravitational potential energy stored in the gravitational field. But when that connection is stretched, let's show that a little bit better. When it is stretched, similar to the way that we would stretch a spring, we're storing energy in the gravitational field, the same way we would store energy in a spring. That gravitational field, when it's stretched, has the potential to set this object, this football, for example, into motion if we release it. Similar to if we release a spring, it's going to go into motion. If I release this football, I know that my football is going to fall and accelerate towards the Earth again. It's going to snap back. This is an example of energy giving something the potential to go into motion. So what we really have to remember is that objects that are on the ground are kind of like springs that are not stretched. And objects that are elevated are like springs that are stretched. And the thing that's the spring just happens to be invisible. It's this gravitational field that you and I navigate and live in every single day on this planet. So that being said, how would we go about calculating the energy in that field? We're going to use several colors, so I'm going to use several different colors to color code this. I would just be prepared. Our equation is written here. Eg equals m times g times h. So Eg stands for gravitational energy. M stands for mass, specifically in kilograms. It cannot be in any other units. Let's do orange. G is a letter that maybe we haven't worked with a ton, but we know what it is. G is the letter that physicists use for acceleration due to gravity. Now, every planet, even the moon, has a different acceleration of gravity. It depends on the size and mass of that planet. Our planet, planet Earth, has an acceleration of gravity of 9.8 meters per second squared. Now we can round this to 10, but 9.8 is the most precise value that we have. And then the last one, let's do green. H. H refers to our height off of the ground in meters. So now that I've got my equation color-coded, I can fairly confidently start using it in problem solving for gravitational potential energy. So let's do this example here on the left. So how much gravitational potential energy is stored in a cliff diver Earth system if a 75 kilogram cliff diver, gosh, I thought that was going to say cliff for a second. If a 75 kilogram cliff diver stands at the top of an 82 or 8.2 meter cliff. So already I'm just color coding the information they gave me. They gave me my mass and they gave me my height. Now G is something that they're not going to give me. I'm going to have to assume, since they said Earth system, that my G is that 9.8, or I'm just going to round to 10 meters per second squared. So this might not be information that's given explicitly to us, but it's information that we can assume. So now that I have all of my information, I can start plugging in to the right variables for this equation. I have my G, I have my mass in kilograms, and I have my height in meters. So I don't even have to change the units of anything. I can just start substituting into this equation. So my mass is 75 kilograms times my acceleration of 10 meters per second squared times my height of 8.2 meters. So when I do this, let's see, I'm going to get 75 times 82. I don't want to do that in my head, so I'm just going to pull up my calculator. 75 times 82, get that add out of there, 6150. Okay. So 6,150 joules of gravitational potential energy are stored in this cliff diver. Oh, that's not nice. Let's try again. That's better. There we go. All right, so the next one is a try. So go ahead and pause the video, and once you've completed it, unpause so you can check and see how you did. All right, so I'm assuming that if you're watching the video at this time, that means that you've already attempted the problem. So at what height must an 81 kilogram roller coaster rider be to store 2,000 joules of gravitational potential energy? So let's start color coding here. So blue, they gave me my gravitational potential energy, so that's different. They gave me my mass, and then again, I'm gonna have to assume that I'm on Earth because that's the only planet I know of that has roller coasters on it. Maybe there are others out there, but it's the only ones I'm actively aware of. So this is enough information. I guess I might be able to plug into my equation and start substituting. But let me see, just to be sure that I'm not missing anything. So I've got my G, I've got my M, and I've got my E over here. So that's everything except for one, which is perfect. That's exactly what I need. So 2,000 joules is going to equal my mass of 81 kilograms times my acceleration of gravity, 10 meters per second squared, times my height. So right now I want to undo what's being done to my height so that my height can be by itself. So right now height is being multiplied by 81 and 10. So I'm going to undo that by dividing by 81 and dividing by 10. So I'm going to do that on both sides. I'm going to divide by 81 and divide by 10. That's going to cancel out my 81 and my 10 over here, leaving me with just height. So now my calculator, I have to plug in 2,000. Gosh, these ads are a nightmare. Go away, ad. Doesn't look like it's working. Oh well. I'm going to do 2,000 divided by 81 divided by 10. Gosh, why isn't it going away? Oh, there it is. Okay. I can't tell if I did this right, so I'm going to have to clear it all over again. 2,000 divided by 81 divided by 10 gets me 2.46. Well, I guess 47 meters. Now you could have rounded your answer to 2.5, and that's acceptable. What I would not do is write all of these numbers. I wouldn't write all of these digits, and I wouldn't round it to a whole number. So as long as you're reasonably rounding to either the tenths place or the hundredths place, you can be fairly certain that your rounding is just fine. just fine. So that concludes this lesson on calculating gravitational potential energy. So go ahead and get some practice while it's fresh in your mind.